Hi, in this video I'm going to explain this tutorial that's contained in a Jupyter notebook, Tutorial 3 classification using simple statistics. Now statistics and machine learning are very closely related. I like to say that machine learning is simply statistics plus high-powered computing. But these simple statistical methods are still important within the context of machine learning. So in this particular video, we're going to talk about using thresholds. Now, what is a threshold? A threshold is a level above which you make one decision and below which you make another decision. So thresholds are very common in classification. If I classify between two classes based on one continuous variable, then typically I will use a threshold to distinguish between the two classes. And we'll see how that works below. So this tutorial will show you how to use Python code to implement and evaluate a classification method applied to a data set, that is our Rooibos data. Current classification methods can be categorized either as basic statistical methods, machine learning, or deep learning. In this notebook, we will use two classical methods, thresholding and Mahalanobis distance. In this particular notebook, we will look at thresholding. Right. Besides using classification methods, it's important to evaluate the performance of each method. In many cases, one of the two classes of particular interest. In such cases, there's a trade-off between positively identifying all instances of this class and avoiding positives. Sorry, I had to change this. This should be avoiding false positives. So again, we'll explain these two ideas later on below. This trade-off is expressed in terms of two important concepts, recall and precision. So you may have seen these two before. When the two classes are equally important, the overall classification accuracy is often used as a measure of performance. As with any parameter estimation, it's important to put error bars on your accuracy estimates. For this purpose, we will introduce the jackknife method for estimating standard deviations of estimators. As its name suggests, the jackknife method is a very useful general purpose tool, can be applied to a wide variety of estimators. So in summary, we are going to address this issue of correctly identifying positives and avoiding false positives and displaying the trade-off between these two. As we said before, this is related to recall and precision. If recall is high, then most of the positive instances have been correctly identified as positive. If precision is high, then most of the instances that are identified as positive are actually positive. I like to think of this in terms of fishing with a net. If you want to have a large recall, you get a large net and cast it widely, and you pull in all kinds of fish. Some you don't want, some you want, but you get most of the ones that you want. On the other hand, precision, you cast your net in a very specific place where you have a good chance of catching the type of fish that you want. So recall means cast. If you want high recall, you cast a wide net. If you want high precision, you cast your net precisely where you are getting your positive instances. And the second issue is, when you talk about accuracy or precision or recall, any number in science has an uncertainty attached. So you need to give an uncertainty estimate together with every estimate of recall, precision, or accuracy. This is important, although it's often neglected. But this jackknife method is a good way to obtain error bars or error estimates for different parameters. Okay, let's go down. All right, so this is just an overview of classification problem. Suppose you want to identify animals. So you have cats and mice, and you want to determine which is a cat or a mouse based on weight or color. So suppose you have animals that you know the weight and the color, and you want to estimate whether that's a cat or a mouse. So these would be the features, weight and color. You'd have some kind of model that relates weight and color to the type, and then that model would give you an estimate of which type of animal it is. Now, of course, weight will count more than color, but here you have a orange animal that perhaps weighs 1 or 2 kilograms, and your model tells you that this is a cat with 98% probability and a mouse with 2% probability. So that's one representation of how classification may work. Now, of course, since cat has the higher probability, you will determine that this animal is a cat. So the final outcome is simply the classification, cat or mouse. But often in classification methods, a probability is also attached. Now what we're going to do is, using our t-samples, we will take individual features and use the individual features to try to determine whether the t-sample is fermented or unfermented. Sorry, I skipped too far. So here we've got binary classification errors, false positives and false negatives. So false positive is when you get a positive result for a test when you should have received a negative result. Okay. For example, if you're screening for cancer and it comes back positive, but in fact the patient does not have a disease, that's a false positive. Now, false negative is when the test result is negative, but in fact the item is positive. For example, if a false negative would occur if a guilty person was found not guilty. In the context of COVID, false positive would mean you test positive for COVID when you don't have COVID. False negative would mean that you have COVID, but you tested negative. Now, in the case of COVID, false negative is much more serious than false positive. So the tests were arranged so that the false negative probability is small. The false positive probability was much larger. Okay. So false positive and false negative have associated false positive rate and a false negative rate. False positive rate would be what proportion of positive identifications are actually negative. Okay. So these are the ones that are identified as positive, the proportion that are actually negative. And false negative would be what proportion of negative identifications are actually positive. So these two concepts are symmetric. False positive would mean what proportion of zeros are classified as ones. False negative would be what proportion of ones are classified as zeros. Now, as we indicated, these two work against each other. Decreasing the false positive rate tends to increase the false negative rate. And then when you get to your notebook, you can click on these internet links to see the relationship between false positive rate and precision, and false negative rate and sensitivity. Okay. All right. So let's look at an example of data where we have a single parameter that takes continuous values from 0 to 1. Now, if you're familiar with logistic regression, the logistic function will determine a value between 0 and 1. And you set a threshold. Typically, with logistic regression, you set a threshold of 0.5. But you can set your threshold somewhere else. It's not fully determined. Right? So let's take this example where we have two classes. Here we're looking at spam. Some emails are actually spam, and some emails are actually not spam. And these two types of emails will have different values on the logistic regression scale. Right? You have some model that determines the logistic regression value, and this is showing the logistic regression value on the scale from 0 to 1. Right? Now, suppose I set my threshold here. So I determine, or I decide, that everything below this threshold is a negative, or it's not spam, and everything above this threshold is positive, i.e. spam. Okay? Now, if I set this threshold, you can see there are two red, which are actually not spam, that were classified as spam. So these are false positives, two false positives. On the other hand, there were three spams that were classified as not spam. So we have three false negatives. Okay? And you can see that no matter what threshold I set, I will get false positives or false negatives. Right? If I set my threshold way up here, then I will not have any false positives, but I'll have a lot of false negatives. If I set my threshold way down here, I won't have any false negatives, but I'll have a lot of false positives. All right? So this is showing the trade-off between false positive and false negative. All right. So for this particular threshold, you can count the number of true positives, the number of true negatives, false negatives, and false positives. You can simply count from this picture. So the precision, also called specificity, measures the percentage of emails flagged as spam that were correctly classified. Now, precision is the same thing as true positive rate. I take all the ones that were classified as positive, and I take the proportion that are truly positive. So the ones that were classified as positive is the first row of boxes here. So that's where we get the 8 for true positive. 8 plus 2 gives me the total number of instances classified as positive. On the other hand, recall measures the percentage of actual spam emails that were correctly classified. So in this case, we look at the ones that are actually positive. That's the first column. Okay? Some of them are classified as positive. Some of them are classified as negative. You can look at the green dots up here. There are 11 green dots. 8 were correctly classified. 3 were incorrectly classified. So I want the proportion of all the actual spams that were identified as spam. So that's called the recall. Okay. That's not the same thing as true negative rate. Then the accuracy is correctly classified over the total number of instances. So accuracy is the 2 green boxes divided by the total number of instances. Okay. And there are various times and various circumstances in which these different quantities are important. All right, and here's the answer that you need to consider. Based on what I've said, you should be able to answer that question. Now, as I mentioned, there's a trade-off between true positive rate and false positive and false positive rate. So the receiver operating characteristic curve gives me this trade-off. Gives me a good representation of how I can exchange between those two quantities. Okay. As it says here, receiver operating characteristic curves are used to determine threshold based on the trade-off between false positive error and false negative error. Two types of errors, and they work against each other. Okay, the ROC curve actually shows something slightly different. It represents the proportion of negatives that are incorrectly classified on the x-axis versus the proportion of positives that are correctly classified on the y-axis. Now, if you think about it, and we'll see this later on, these two proportions will increase together. The more positives that are correctly classified, the more negatives will be incorrectly classified. So the ROC curve is always an increasing curve. So we'll be using different packages that we need to import. So the import is done for you. Now, in the first Jupyter Notebook, it explains how to recover previously stored data. And you should know by now how to display the shape and the first two lines of a data frame. Okay. Now we want to create arrays for the inputs and outputs. And this is done for you. We take the features that are H2O and the features that are MEOH. MEOH is methanol. Now, it's very important that you correctly rename these variables in the first sheet. If you did not, you'll get a wrong answer. So it would probably be a good idea to check that feature H2O has 3 columns and feature MEOH has 3 columns as well. And this is the output. We know the output is either 0 or 1. Right? DF is the combined data frame that includes both fermented and non-fermented. Now, we consider the case where we're trying to use individual features to distinguish between fermented and non-fermented. Since we have 3 different features, well, we actually have 6 different features, but for each set we have 3 different features. For each feature we can set a classification threshold. So which of these 3 features will give better classification results? We will be comparing these 3 features, the water features, and we will be comparing the methanol features separately. So what we're going to do is get an ROC curve for each one of these 3 features. So you are to complete the incomplete code here. And what you need to complete is you need to compute the true positives and the false positives based on the false negatives and true negatives. Let me explain this code a little bit. Now remember what a threshold does. A threshold distinguishes between positive and negative. So far we've always said that the positives are above the threshold, the negatives are below the threshold. But it could be the other way around. It could be that the positives are below the threshold, the positives tend to have lower values, and the negatives tend to have higher values. So this THR pause indicates whether you're taking a threshold with numbers above being positive or numbers above being negative. If you want the positives to be below the threshold, you should set this as false. Now there are 3 of these values because we're going to be looking at 3 different features. Right. So this just sets the size of the figure. Now what this zip does, think as representing a zipper. You know that a zipper joins 2 things together. The zipper on your pants or a zipper on your jacket. It joins the 2 sides together. This zipper joins the features with the threshold. We do have 3 features that we've defined above, and we have 3 threshold directions. So that means the first feature is associated with the first threshold direction. The first feature was TPC-H2O. The second feature, TEAC-H2O, will be associated with the second threshold direction, and the third feature will be associated with the third feature direction. And those specific values will be represented by F and THP. So the first time through the loop, the value of F will be the first feature, the value of THP will be the first direction. Second time through the loop, F will be the second feature, THP second direction, and so on. Okay? So now, we want to take our feature that we're examining, our feature F, so we take that particular column of the data frame and we flatten it. We don't want it to be a two-dimensional array anymore. We just flatten it out into a single array of numbers. And then we need to record the number of elements in this array, so we take the length. Same thing with Y. We take Y and we flatten it. So it's flattened out into a single array with just one dimension and not two. Now, if the threshold direction is negative, we want to flip the Y. We want to change the direction because we want basically the larger values to be more positive. So if I flip this direction, then the larger values of 1 minus YR will be more negative, and if the actual ones are more negative, this will give me the correct identification. Now in this command we are sorting the values of the feature. Why do we do that? Well, you can see why above. In this picture here, you can see that the values are sorted. Now I could set my threshold on any one of these samples. So what we're going to do is we're going to scan through these samples and set our threshold at each one. But I want to set the thresholds in order. So I want to go from smallest to largest. So that's what I'm going to be doing. These are in order. And I'll be setting my thresholds at different values in order, increasing order. All right. Now to explain a little bit more clearly, I thought I would do an example using Excel. Suppose we had feature values from 0 to 1, which I put in this column A, and suppose the associated Y value is here. So we know that the class is either 0 or 1. So first let me sort the feature values, which is what we did in Python. And we want to make sure that the Y values are also rearranged corresponding to the sorted feature values. So I can take the data, go to data, then go to sort, and I want to sort by the feature value, and smallest to largest, and we have this. Now, I want to take the cum sum. So what is the cum sum? Cum sum is the sum beginning at the first value up to the current value. Now the way to do this in Excel is to use the sum function, and I start with the first value. Now since I want this value to remain fixed, I'm going to hit F4, which makes it a fixed value. Then I want to take the sum up to, so it didn't do what I want, B2, and then I want fixed value, and then I want to take up to, in this case I want to take it up to B2, but then when I do a fill down, you will see it will sum up to the current value. Okay, so this number here, for instance, this 4 says that there's 1, 2, 3, 4 Y values whose feature value is less than or equal to this value. All right? So this cum sum is increasing. It's counting the number of ones less than or equal to this value. So you can see it's actually using this as a threshold and saying if I'm at or below this threshold, I count it as negative. If I'm at or above this threshold, I count it as positive. So the cum sum is the number of ones below the threshold. And that's exactly what I want. That's going to be the number of false negatives. Okay? So this cum sum is giving me the number of false negatives. Okay? Now, what about the number of true negatives? Well, the number of true negatives will be the sum of all the zeros beneath. Now, if I take 1 minus y squared, that will change the 1's to zeros and the zeros to 1's. So let's see if let me insert that. You can see that. I'll insert a column here, and I'll take 1 minus y value. And here I just take equal 1. I'm sorry, I take 1 minus the y value. And then I fill that down. All right, so you can see that whatever's a 1 becomes a 0. Then I take the cube sum of 1 minus the y value. And you can see that this is going to be, sum, beginning at the first one. Fix the value. I'm not sure why it keeps doing that. Fix the value. And then go to C2. And then if I take this down and I fill down, you can see that, for instance, right here, this 4 indicates the number of zeros below this value. Right? If I count from this threshold, I have 1, 2, 3, 4 zeros. Now it switches to a 5 here because a new 0 has been added. 1, 2, 3, 4, 5. And every time there's another 0 in this column, you see that the cube sum increases by 1. Okay? So this is giving me the false negatives and the true negatives below the certain threshold. Now it's up to you to figure out how to compute the true positives and the false positives. Now one way to check is that the true positives plus the false negatives should be the total number of positives. And if that's not true, then you have something wrong. And the false positives plus the true negatives should be the total number of negatives. Right? So you can check your answer. Right? So this is true. So this computes true positive rate. True negative rate is the proportion of negatives that are above the threshold. So so you can complete this also. Then you'll plot the false positive rate versus the true positive rate. And you should get an increasing graph. Now, the plot also shows the 45-degree line. And it says that the 45-degree line counts as guessing. Why is that? Well, on the 45-degree line, the true positive rate and the false positive rate are equal. So you're just as likely to get a true positive as a false positive. So it's just like you flip a coin. If you have a positive, you flip a coin and say, well, this is true positive, or this is false positive. All right? So your classification should do at least as good as guessing. Now, if your classification is below the 45-degree line, something is wrong. And it's up to you to figure out what's wrong if your ROC curve is below the 45-degree line. Right? All the ROC curves should be above the 45-degree line. Right? And then these give some labels and title. You can see how this works out in the final result. All right, so this explains the same thing. Each line in the above graph shows the true false positive and false positive rates for classifiers based on the threshold. The x and y values depend on the threshold that's set. The thresholds are not shown. We only show the relationship. Right? So, for example, if we use the TPC H2O feature and set the threshold so that the false positive rate is 0.3, that is, the specificity is 0.7, then the true positive rate is between 0.4 and 0.5. Now, how do you get these numbers? Well, you should take a look at your graph. Your graph should agree with these numbers. Right? You should have a point on the graph that agrees with this specification. Now, the dotted line corresponds to random guessing. If you simply make random guesses, then the true and false positive rates will be equal. A good classifier will have points with large true positive rates and small false positive rates. In other words, the ROC curve should be above the 45-degree line. And the higher the better. the AUC, area under curve, is an overall measure of how high above the 45-degree line the curve is. So you may see AUC in some papers or some other classification literature. So this is what AUC is. An AUC value of 0.5 is equivalent to random guessing, while an AUC value of 1 indicates perfect classification, which almost never happens. Okay? We can see some of the classifiers give an AUC value less than 0.5, means these classifiers are worse than random guessing. How to solve this problem? Well, you can read this. All right, so then you do the same thing for the 3 features based on methanol. Now the ROC curve does not tell you which threshold to actually use. It only tells you what the true and false positive trade-offs are possible. The user will have to decide what trade-off is best. ROC curves are especially useful if you want to compare different classifiers. Classifiers with higher ROC curves and higher AUC values are better than classifiers with low curves. And then please answer this question. And then we will stop here. We will not do classification using multiple thresholds. That's a little bit involved, and it's really not that useful. When you have multiple features, you typically are not going to use multiple thresholds. You'll use another method. Okay.